Hi everyone, Dave here. This mini lecture's on thermodynamics. What we're going to be looking at is a little bit to do with how energy changes in chemical reactions. That's essentially what thermodynamics is about, hence the title, right? Thermo, energy or heat, and dynamics, movement. This stuff's really interesting because it explains a lot about why some reactions actually occur and why some don't. So let's get into it. First of all, like always, a little bit of terminology that you need to come to grips with, and the first word that I want you to come to grips with is this one, exergonic. An exergonic reaction is one where energy is liberated from a reaction, and that's really all reactions are like this. You can see where the word comes from, exer meaning outside of, and gonic derived from. So these are reactions that are obviously producing some sort of energy. So if you look at a reaction like this one here, where we've got wood burning, really the reaction's a reaction between carbon and to some degree hydrogen and stuff in the wood and the oxygen in the air, and clearly energy is being given out in the form of heat. If we're just looking at the carbon part of things, there's the chemical reaction for it. We've got carbon here combining with oxygen, so these are the reactants, and you're forming carbon dioxide, which of course is the product. You can actually write the equation a little bit differently to what I've just shown you here. You can write it like this, and this is illustrating that in fact heat's given out. You may or may not, depending on what message you're trying to get across to the person who's reading what it is that you've written down, but in this case this one's clearly showing you that carbon and oxygen are reacting to form CO2 and heat's given out in the process. Now this reaction, or sorry, this diagram here is really important, and I want you to be able to get your head around what's happening. Let me walk you through this. I know it looks quite complex, but it's actually not that bad. If we look on the left-hand side here, this is our energy component here, and this is going from a low value up to a high value. If you're having trouble imagining this, imagine that you're standing at the bottom of a cliff, in which case you'd be down here at a low energy value, and if you're standing at the top of a cliff you'd be here at a high energy value. Okay, so what else have we got here? We've got time on this axis. So what this time represents is the time taken for the reaction to occur. In other words, as you move along this axis here, the reaction's progressing. So what that means is at the beginning of the reaction, what we've got present are reactants. There are no products, it's just simply the start of the reaction. So now we can start looking at this part of the diagram here. So here's our reactants. Here's our reactants here. Okay, so we're just starting off the reaction, and here's the amount of energy they're sitting at. Just there like that. So they're standing at this part of the cliff, if you like. They're at this particular energy level. I'm going to ignore this hump for the moment, so I want you to do that also. What I want you to do is have a look at where the products are sitting in terms of their energy level. They're actually sitting lower. So reactants are reacting and they're forming products like this, and the products are at a lower energy level. Now there's a law called the law of conservation of energy, which is in a way kind of similar to the law of conservation of mass, and it says that energy is neither created nor destroyed. So if I start with this much energy in the reactants here, and I end up with this much energy in the products here, the difference here between this and this must have gone somewhere. So there's energy here that's actually being released, and that's the difference between them there. And you often see that in terms of things like heat, right? In this particular diagram there, they've called it the profit, if you like. So all that's good. Clearly, the bigger the difference in energy levels between the reactants and products, the more energy you can get out of the system, which is kind of nifty. So it's not surprising that things like petrol, for example, when you burn it in oxygen, you produce large amounts of energy, and the reason for that is because the oxygen and the petrol are at a very high energy level, and the products that are produced, mostly carbon dioxide and water, are at a quite low energy level. The other part of the diagram that's important is this one here, this hump thing. So what's happening here? Well, for the reactants to react, they don't just simply go to products, they actually have to get up to a high enough energy level so that they start reacting. Once they get up to here, they can then fall down the other side and produce products. So you often have to put energy into the system in order to get the reactants to start reacting. What's that energy called? It's called the activation energy. There it is there. This kind of transition period here, where things are no longer reactants nor are they products, this is actually called the activated complex, and I'll just abbreviate that as AC, because if I tried to write it, it would look horrendous. So that's the activated complex there. Now this part of the graph's really interesting because it actually determines how stable things are, or if you like, how fast they'll react. So if you've got only a little hump for the reactants to get over like that, you can imagine it doesn't actually take much for them to react. There doesn't have to be much of an energy input here at all. So what this means is that for these sorts of systems where you have low activation energies, you can have quite unstable compounds. These things here are quite stable. Now this explains the interesting observation that you can have compounds that appear very, very stable, and yet when they react you get out large amounts of energy. You can see why, because there's actually two different effects going on here. The amount of energy that's given out is due to the difference between reactant and product energies, but the stability is due to the difference between the reactants and the activated complex energies. So that's actually an extremely useful diagram. Just to give you an example of how you could apply this kind of idea, if you look at an explosive compound, all explosives of course are giving out large amounts of energy, so the difference in energy between reactants and products is very, very large, but some explosives are more stable than others. So a classic example would be the explosive called C4. In order to get that to actually detonate, you actually have to pretty much explode it to start with, and you use a detonator. So its activation energy is really, really high like this. So it's very stable. You can slap it around, and I think you can even shoot it and it won't explode. But another explosive like nitroglycerin, whilst it would give out similar amounts of energy to C4, it's got a very low activation energy, and therefore it's very unstable. What this means is that you can actually get nitroglycerin and simply tap it, and if you tap it hard enough, you'll put enough energy into the system to get it over this activation energy barrier, and then you'll get an explosion. Okay, so there's just a little summary of what's happening. I'm not going to go through that right now. Okay, so, and again another little summary, and I've even got a couple of YouTube videos there for you to have a look at, showing you the difference between things like nitroglycerin and C4, and you should now be able to relate it to that activation energy diagram. Now the final thing I just want to point out to you is what catalysts do. Now there's two ways you can look at trying to get something to react. You can either pump energy into it in order to get it over that activation energy hump, or you can actually lower the activation energy itself. And that's what catalysts do. So they're things that speed up reactions. They're not actually consumed in the reaction. They simply speed them up, and they do so by dropping the activation energy. So here's a classic example here. You can see there's no difference in the energy levels of the reactants and the products, they stay exactly the same, so you'll get exactly the same amount of energy out whether you use a catalyst or not. But here's what originally happens. There's the activation energy hump, but you add a catalyst, there it is there, and the activation energy hump decreases, so therefore it's much easier for those reactants to get over that hump and form products. So the classic example of a catalyst would be things found in biology called, or in cells called, enzymes. They're proteinaceous molecules, they're proteins, and they can act on things as catalysts and then speed up reactions very, very fast indeed. So for example, there's an enzyme in your saliva called salivary amylase, and it breaks up sucrose, this particular sugar molecule that you find as table sugar. And sucrose itself, as you know, table sugar is very stable. It can sit on your shelf in your pantry cupboard for literally years and nothing happens to it. But the moment it goes into your mouth, the salivary amylase will lower the activation energy here, and the sucrose will break down and form products. And there's the example, there's the actual chemistry. With, by the way, salivary amylase is sometimes called sucrase. There it is there. We start with sucrose. What happens is a water molecule is added and it splits it into two smaller sugars. Another example is this enzyme here, catalase. It actually acts on hydrogen peroxide, and the hydrogen peroxide is broken down into water and oxygen. And you can actually, well, I wouldn't encourage you to do the experiment, but for example, if you buy teeth whitening agents and you put them around your teeth, you'll feel a fizzing going on, and that fizzing is actually due to catalase in your tissues reacting with the peroxide that's present in that whitening agent, and the peroxides being broken down and producing oxygen, and that fizzing, bubbling feeling that you get is actually due to the oxygen. And it's that oxygen then that's actually bleaching your teeth and making them whiter. Okay, that's it for this particular mini lecture. Hope you enjoyed it. Bye.